Good morning, mathematicians. Hope your week's started out full of proofs and understanding. And not weird pieces of fluff in your keyboard. Yeah. Ooh, new sheafification of G video. That's a good day. Hope your week's started. It's a real good day. I bet you a lot of people are thinking I won't be here. Oh, Edit Smith, you're already here. I was just about to say, I bet a bunch of people aren't thinking I'll be showing up till like 8:30. But I'm early today. Or am I on time? And did I used to be late? Hey, 314 calls. Nice to have some people in stream right away. I guess probably go to Reddit to start to see if there's any conversation starters here. And then I might rant more about D modules. We'll see. We might collectively read through some notes on D modules, maybe, if people want. Well, we'll see if we have questions. Oh, did I freeze? Oh no. I'm hoping the stream didn't freeze, and that was just Reddit being weird. What are the prerequisites? This story here doesn't. I don't know. I feel like there's more details. You gotta learn more D module stuff for sure. Well, yeah, maybe we'll talk about it. But yeah, this can I talk a bit about hyperfunctions? No. I've learned about them before at some point. Well, actually, I mean, I shouldn't even say I've learned about them. I've read about them at some point, and I forget everything. We could maybe read the wiki page together. That's the best I could do for you today. Yeah, but this post is weird. Like, too trivial. Okay, like, I could imagine a reviewer saying that. But then, so you generalize it, submit it, and then, oh, they just say too complicated? Like, I don't know. There's probably more going on. But anyways. Yeah, let's look at what even are hyperfunctions. What even are hyperfunctions? I remember first learning about them from Roger Penrose's Road to Reality. He has a section on hyperfunctions. Oh, nice. Oh, I think you said that at the same time I did. Recently found my channel, big fan. Awesome. Great. Glad to hear it. Welcome to the office hours. Oh, starting a master's soon. Nice. Do you know what your master's will be about yet? Yeah, so hyperfunctions, right. Generalized functions, right. Somehow something to do with... Yeah, I don't want to say anything stupid. As a jump... there's a question. I just wanted to ask, in Masters in Math, better to M.Tech in computational data science, more valid for quant finance? I'm not exactly sure I understand the question, but yeah, if you're asking about quant finance, and I mean, there's... Well, I don't know. There's specializations probably within it, but like you can just do a master's in quantitative finance, I'm pretty sure, and then you would from within that, I imagine you could specialize to like research side versus like what are the typical quant roles like you've got research and trading and stuff, and then like you could specialize from there. You work as a data scientist now. Oh, cool. So probably something computational mathematics side. Nice. Well, there should be some interesting things from data science you can apply to all sorts of stuff. Very much not applied, but I think there's cool stuff happening with statistics and number theory. Please try to make it soon. Yeah. Well, I don't even know. I don't even have a quant person in mind who I'd interview. Maybe I could interview some YouTuber. Maybe, I mean, I don't know. A lot of these other YouTubers already talk a lot about their own journey. But I've watched some of Dimitri Bianco. I think that's his name. I've watched a bunch of his videos. Maybe he'd want to do an interview on my channel. I don't know. Maybe his channel. Maybe it's too big though. His channel's too big. I got to get someone more in line with my own. I don't know. Hyperfunctions, generalizations as functions as a jump from one holomorphic function to another at a boundary. Okay, that makes sense. And it could be okay. I was worried I was gonna say something stupid. As I was gonna say earlier, I recall they have something to do with distributions, and indeed they can be thought of as distributions of infinite order. Informally, though, apparently. Okay. I think speaking of D modules, I think these things do have something to do with D modules, because I was recently reading a thesis of a previous student of my supervisor who worked more on the D module perspective from the stuff that we do. And later in the thesis there is stuff about hyperfunctions. Yeah, I do remember this sort of notation from Penrose's book. Informally, the hyperfunction is what the difference would be at the real line itself. The difference is not affected by adding the same holomorphic function to both f and g. So if h is a holomorphic function on the whole complex plane, these hyper functions are equivalent. Makes sense. And we've got a fancier version here. Motivation can be concretely implemented using ideas from sheaf cohomology. Define the hyperfunctions on the real line as the first local cohomology group. Okay. So if we let C plus and C minus be the upper half and lower half planes, then, so the cohomology will be, why will it be that? Well, I should probably go read an actual book on this sometime. Probably never. Okay. What should we do? Maybe I should just bust out the D modules book, and we should go through some of that. And until there's other questions. Well, really, this isn't a book on D modules, but I like the chapter on D modules. So let's take a closer look together. Okay, so starting your bachelor's thesis, recently started getting into fiber bundles and topological K-theory. I'm currently working with the Husmoller book. Do you know any other good references? Yeah, I personally found that book. I think I tried reading that book once upon a time, and I found it very hard to read, just based on like the background I'm coming from. Um, but what are other good references? I wonder actually. One of these days, I should make a video going through all of my old math courses and all of my notes. Uh, Differential geometry. No. I had a project actually in a rings and modules course that involved um, vector bundles. I thought I had some notes in there. No, it doesn't look like it. What are good notes on vector bundles? Well, I did buy myself a copy when I was trying to study vector bundles more of Steenrod's original book. But I don't think that's a great resource to learn from. I wonder if I just search up if I can find the PDF that I used. Vector bundles PDF. I wonder if any of these. Did I use Hatcher as notes on vector bundles? That must be his like a characteristic classes thing. Vector bundles and their applications. Yeah, I don't remember now. No, none of these were the notes that I used. That's kind of unfortunate. Because I do remember one of the sets of notes that I had. Oh, good morning, Sarks. One of the sets of notes that I had did have something Milnor Stasheff would be the standard reference. Okay, well then probably go with that. I would. I do remember this. Vector Bundles and K-Theory by Hatcher. Yes, I do remember. I do remember. This is one thing. The magic stream. Yeah, we were talking about the Turing complete ness of magic. Incredible stuff. Yeah, I did actually. Now that I'm seeing this, I do remember looking at. I think this book is still incomplete. Is it even? Yeah, not yet written. I don't think that's changed. I mean, this is a random PDF I found. So yeah, I remember looking at this when I was reading some vector bundles and topological K-theory stuff. But people have divided opinions on Hatcher, but it was a useful reference for me at the time. But I would, I'd trust if matrix coefficients says that it's standard reference, and I would maybe look at it. Milnor Stasheff is characteristic classes. Looking for more cohomology K-theory stuff. Well, I mean, those things are very related, right? Like, there's, characteristic classes are things in cohomology, and they have like a axiomatic definition in that sense. And certainly, like, they do actually, characteristic classes I think are also related to this isn't the book I looked at either, but they're also related to K-theory. Like, if we look at the full growth and Riemann-Roch theorem, the full growth and where do we have the K ring? Oh, maybe it's just K0, which is, again, that's like the only K theory I do, and this is much more interesting. But Why don't they have a nice, pretty picture of the commuting diagram here? That's silly. Someone's got to fix this Wikipedia page. Yeah, I mean, anyways, like the churn class is, like that gives you a map from K0 to the Chow ring. The total. So I think this is the total churn character. Yeah, I would assume that there's a higher version of this as well. So those things aren't unrelated. I would say, but there's yeah, probably you can dive more directly into, like, if you want to understand some basic stuff about topological K theory and vector bundles. I would look at this sort of extra, this little mini incomplete book from Hatcher. Oh yeah, clutching functions. I remember I was trying to understand those because there's actually, isn't the higher version some index theorem stuff? I think so. I don't know. But that sounds right. I mean, I think the original version is even some index theorem type stuff. Yeah. But yeah, I remember. Okay, I should let me bring up my old documents, my old course notes again from Rings and Modules, because I did a project on. Let's see if I have the paper. Construction of octonionic polynomials. Yeah, I think this is it. Oh no, he's just talking about the construction. So this project, are EGA still in print? Good question. I don't know. You should just go by Vakil's notes. There's a hard copy now. Beautiful cover, beautiful set of notes. Oh yeah, here we go. Here's the paper. So check out this paper. It's a proof of the fundamental theorem of algebra for octonions, which I talked about in a previous stream. But it uses the theory of like K theory and vector bundles. So yeah, this paper is a revision of a portion of the author's doctoral dissertation, using elementary concepts of K theory. The Brouwer degree of the power map in the octonions is computed. Later, a weaker version of the fundamental theorem for algebras with coefficients in the octonions is given. Yeah. So, yeah, part of my... Actually, yeah, funnily enough, this probably should have been a project in a differential geometry course, but it was a project... I took a course on rings and modules, and then a big focus in that course was talking about polynomials over non-commutative rings. And we discussed... Did we even prove possibly the fundamental theorem of algebra for quaternions? And so naturally I was asking about the... one day after class, I was asking about the fundamental theorem of algebra for octonions, yeah, the professor was like, "Oh, that's maybe a good idea for a project." But so then I ended up reading a bunch of stuff about like vector bundles to try and understand this paper, which I don't think I understood a lot of at the time. But I made it sound like I did in in the document. No, I mean, I understood some of it. It wasn't that bad, but I was definitely punching a bit above my weight class then. Yeah. Yeah, I mean, I don't know if you guys know this also. There's this connection between the only... parallelizable spheres and the normed division algebras. Like there's some relationship, and I think you can even prove something about this with characteristic classes, by the way. I think there's some relationship. So we've got like the real normed division algebras, right? Reals, complex, quaternions, octonions, and then there's some relationship. I think. What are the spheres? It's like S. What is it? S7, S3, S2, and S1. Are those the or maybe this is S1 and this is S0 or something. There's some like relationship with like the parallelizability of spheres or something, and these. It's kind of like it's a deep result actually. And I think there's like some of the proof, a terse version of the proof in Peter May's concise course in algebraic topology. Do I know if the ideas also work for other real division algebras or only the octonions? Would be interesting either way. Yeah, I don't know really. I mean, I think part of the idea is that, like, I think S7. Part of the idea. So one of the ways that you go through this is because like there's interesting things about like relating cohomology groups when you have like fiber bundles, and so I think you do things like. Gosh, what is it? So I think you've got like there's some relationship between the quaternions and the Hopf fibration, if I'm remembering correctly. So there you've got, what is it? Yeah, so it's S2 as a fiber bundle over, sorry, S3 as a fiber bundle over S2 with fibers given by S1. And so this setup somehow corresponds to the quaternions, and then the octonions. I think is S7 up top. Yeah, maybe there's some other bundle of spheres, and another way to phrase this in terms is like classification of like spheres that are fiber bundles of spheres or something like this, and there's some. Yeah, relationship. There's some sort of strong like you can prove one of the classification theorems in terms of the other. Like you can prove that these are equivalent. And I'm tempted to say though that I know this is S7, but like the octonions naturally show up in S8, and then I think there's some relation here. So. Yeah, I don't really. I remember that being some step in the process. That might even appear in this paper here somewhere. Well, you can see the use of S8 here, right? I mean, the octonions are in 8-dimensional space, so you take the norm 1 octonions, and you're going to do something with that. Like if you think about the same way that you prove the fundamental theorem of algebra. For the complex numbers, you're taking something with S1 in the complex plane, but yeah, it's not so clear to me. Like, yeah, it's not so clear to me. Well, I think maybe I think maybe also the reason why this comes up with the normed division algebras, right, is that exactly like you're relating the norm 1 things in each of these algebras, right? And that's what allows you, right? So this should be S0, I think, and this should be S1, and this should be S3, right? That makes S3. I don't know. That makes sense. But Is it S3 or is it +1 and everything? Anyways, if I'm recalling correctly, I think the crux of the matter is because we specifically have the added feature of a norm in each of these cases. That's how we're allowing we're able to define connect the norm one elements in each of these things to actual spheres. So I think if we just had other real division algebras not necessarily equipped with a norm, yeah, I don't it's not clear to me that the same thing would work. But I don't have an intimate understanding of the proof, so I could be wrong. There could be other ways, other workarounds possibly. Oh, I should probably plug in. Apparently it's better while I'm live streaming. Okay. Yeah, homotopies of maps into rotation groups. Yeah. Yeah. So there's There's like okay. Right. So the one corresponding to really I thought the original hop vibration corresponded to the octonions. Maybe that's true, but I guess is this what it is for the octonions? Is it's determined by the base? Interesting. The dimension of the base. So then shouldn't the Yeah, I don't know what I'm saying. Right, but we see, very similar thing of the hop vibration being used. And then here's where the K theory comes into play. There's some use of what the K rings are here. The original hop vibration is from C. Yes, yeah. The original hop vibration is yeah. It is. I mean, it is what I wrote. It's a bunch of S1s. It's a bunch of your base space is S2, and you have a bunch of S1s, and then that fiber bundle is it gives you a manifold diffeomorphic to S3. But I was just not sure because I know I was thinking about which of these like sphere bundles is supposed to match to the quaternions. I'll probably look it up. What sphere bundles division algebras? I thought there was a nice Wikipedia article about it that had the pictures of the diagrams. No. Intuitive way to think about the... Yeah. Okay, I mean, here's the statement that these are parallelizable. The parallelizable sphere is connected to these things, but there's some relationship between the... I guess you could call them the generalized Hopf vibrations. I can't remember like each of these. Whatever. Each of them appears as the. I can't remember if each of them appears as like, I guess the fiber. Anywho. Yeah, so I think this is a really cool paper though. I should maybe go back and reread it. I think it'd be a lot more understandable to me nowadays. Actually found out there was I don't remember how I stumbled across it, but I randomly stumbled across there was some other proof. There's a professor at my university, and she wrote a paper, I think with one or two other people, and they also give a proof on the fundamental theorem of algebra for octonions using other techniques of algebraic topology. So, very cool stuff. Yeah. So, where do we go from here? I guess we could talk a little more, slowly make our way through D modules here, as I need to digest these things better. So, well, as we're told here, right? The D modules are basically, so we've got an algebraic variety. Let me write some things down. We've got some complex algebraic variety, and we've got our sheaf of rings, and then we've also got theta x, which is our sheaf of derivations, which is that should be which is certain subsheaf of this sheaf. And our derivations, I mean, normally we think of those as, well, sort of derivatives. And, the classic example is like if x is a1c, or, maybe we should call it spec of cx. Well, then, in that case, our ring of global functions is going to be cx, and our I should say this is like the global sections. I mean, it's an affine scheme, so the sheaf is totally determined by the global sections here. So it's but still, let me write this. OXX, let's say, is just our ring of polynomials, and our derivations are just a ring in the derivative of the formal derivative of polynomials. And so I guess the way we normally write it as dx, our ring of differential operators, globally dxx will just be the non-commutative polynomial ring generated by x and delta modulo. I think I mentioned before on stream. Is basically, it's just the relation. It's just the relation that has this act as a derivative, right? I always forget which way it goes, so I have to write it out. I have to pretend there's a function here and do the Leibniz rule. This plus wait, what am I doing? Yeah. Plus f time. Yeah. Right? Right. Right. So it's x del minus del x plus 1. Take that quotient. Yeah. I think we view this as a left ideal. I thought part of me thought it was supposed to be a two-sided ideal, but then Achara said something about left ideals, so yeah. Right, and sure enough, that's exactly what we see down here. This is also called the first Weyl algebra. And then there's another example for the punctured plane. Okay. And then we have the order filtration. So it'd be nice if I could just like copy paste this stuff into my OneNote. So a D module is kind of like a sheaf of OX modules such that we know how to apply differential operators on its sections. Yes. Sounds like a sheafy version of a vector bundle with connection. That's because it literally is. Let me jump ahead. So if you have a coherent OX module, which is the algebraic geometer's vector bundle, equipping M with an integrable connection is equivalent to giving it the structure of a dx module. There you go. Yeah, so I should say, I guess I didn't fully define what a dx module is yet. Rather, so I defined what I did define was the sheaf of differential operators, but a dx module. Well, I guess it's right in the name, right? So I've defined. I talked about what the sheaf of differential operators is. So a dx module is, well, a module in the sheaf sense for this sheaf of rings, basically. I think we might also impose that it is OX coherent. That might be part of the definition as well. Does the char say this? He talks about the order filtration on dx. I think he says this, though. Oh, hi, Nicole. Does he not actually define D module? Surely he must. No, maybe we don't need the coherent stipulation. No, we don't need the coherent stipulation, but we do generally impose it. We're going to impose it later. That's right. Yes. Yeah, exactly. Okay. And then the order filtration, well, why don't we work out an example of this? So the zeroth filtration of dx will be just the global sections. So in our example, that will just be cx. And then we have the relation. Let me see here. I have such a bad memory. Fp minus 1. So Fp dx will be Fp minus 1 dx plus the sheaf of derivations. And what was it? Fp? Got no memory. That's also Fp minus 1. Okay. Oh, Colton, is that the Colton that who I met in Moraga? If it is, nice to see you. Yeah, I mean, fantastic book. I've been discussing this book plenty. Sorry, maybe I shouldn't ask you that if you're worried about like doxing yourself or something. Maybe it's not a good. I should have asked it in a more subtle way or something. But, um, anyways, I've been the one and only. Great, good to hear. By the way, side note. So Colton, we discussed in Moraga. Um, Starting mentorship programs, and I was talking with you because you had mentioned that you had started a mentorship program at your institution, and so I did the same actually in the fall, and I've had now two separate. I had one that sort of ran and ended in the fall, and then I had a new one that's, I guess, coming to a conclusion soon for this semester, and they've both been going fantastic. So, thank you is our discussion there about it, that sort of helped prompt me to finally, um, hunker down, just get my stuff together, and make the program happen. And it's been great. The grad students and undergrads alike seem to have really been enjoying it. So, yeah, cheers for that. Um, yeah. Just joined. Am I enforcing Leibniz? Which manifold is trivial? Is X trivially defined on this manifold? Yeah. So sorry. In this, I'm. I guess to be clear, I'm jumping back and forth between uh, being abstract and some concrete examples. So, uh, what am I trying to say here? Yeah. So like in general, um, the the sheaf of derivations, like these are maps. These are basically defined to be like maps between the structure sheaf that say at each, um, what do I call it? So for each u, let's say, like the map that we get here, phi u, does need to satisfy the Leibniz rule. I mean that's basically what it means to be a derivation, right? So, uh, sorry to interrupt. Feel free to talk about this later or in another stream, but do I know about quiver varieties? My advisor suggested it as a theme for my master's. Yeah, well, hey, I mean, I'm definitely open to. We're all about interruptions and sidetracking on the stream. Yeah, I know a little bit about quiver varieties. Other people in my research group know a bit more because they focus on that perspective. Um, but actually, so I don't know if you I'll come back to this in a second. Um, but previously, I've talked about how one of the sort of the things that my research group studies are these varieties, which we call Vogel varieties, or V for vendetta, and we're trying to study singularities. We're trying to study singularities in these things, and somehow those singularities feed us information about the representations. I mean, these are somehow, by passing through the local Langlands correspondence, these singularities are supposed to tell us information about these representations. And it turns out, actually, that in many cases, I don't want to say all, but in many cases, these V's actually turn out to be examples of quiver varieties. And so one of my colleagues in my research group, he one of the tools that he uses to analyze these things is the fact that these are quiver varieties. And just because this is such an amazing book that I plug all the time, let me jump over to here we go. Quiver representations in quantum groups. So chapter 10 of Achar's book has stuff on basic stuff about quiver varieties and quiver representations. So definitely cool stuff. Definitely cool stuff going on here. I would recommend. This is probably like Gabriel's theorem. Well, it's like the classification of simple Lie algebras. So that's probably a good thing to like aim to understand. But yeah, so yeah, this is one of the books I can't recommend enough. So let's jump back and just work out this example explicitly. What our filtration is given by here. Oh, got some more questions. Achar's great. Didn't even know it talked about D modules. Yeah, it's kind of buried in there. Yeah, because it's not. Yeah, I guess it's not one of the big focal points, but lots of goodies in there. So, we already know what F0 is by definition. So we'll take a look at what F1 is. How are math competition questions different from research math, and is there any connection being good at one implying being good at the other? Well, I mean, the most fundamental difference, of course. Oh, this should be dx. What am I saying? What am I doing? The most fundamental difference, of course, would be that questions in math competitions have known solutions, and research questions do not. So, that's a pretty big one. Is there any connection of being good at one implying being good at the other? I mean, no. Like yes and no. Like the common the analogy that people give is running a sprint versus running a marathon. Oh, I've started writing nonsense already. Running a sprint versus running a marathon, which is certainly true. But I mean, also like, go look at who's won a Fields Medal in the last however many years, and then go look up like gold medal math Olympiad winners, and I mean you'll see some common names, or I mean just like go look up gold medalists, list of gold medalists from the math Olympiad, and you'll see a lot of famous names just in general. Now that doesn't mean that doing math competitions makes you good at sorry, I'm trying to think about too many things at once. But that doesn't mean that math competitions make you a good researcher. It just means that generally math competitions are something to do when you're young that gets you interested in math and builds a lot of skill sets. And so people who are have a talent, if you're going to be the best in the world, most likely you're going to have a talent at a very young age, and that's going to be discovered at a very young age, right? So I wonder if I made a mistake here in the filtration, because I thought that F1 was supposed to be the order 1 differential operators. Uh, but I don't think I want constants in here, do I? But yeah, so too many thoughts at once. So certainly there is a connection. Anyways, that is I guess the point I was trying to make. You can still be a great mathematician without ever having done competitions, but yeah, there is reasons why those things are correlated. Do I listen to anything while I'm working? Do I think it's bad to listen to music? It totally depends on the day and the mood. Oh yeah, duh. It's a filtration, so it'll contain F1 and F0. Right, right. It's supposed to be the quotient that gives me, each order of the differential operators. Right. But yeah, when it comes to listening to music, it totally depends on the day. There's some days where I need total silence to have perfect concentration. There's other days where I need like hard, intense math rock. There's other days where I need chill, lo-fi hip hop, whatever. Yeah, and the same work could, like, it depends. Yeah, it really depends on what I'm doing, and my mood and brain state. Yeah. Let me just see here. What have I done? I don't think I did anything silly, but yeah, the order filtration of dx, fp dx. Yeah, okay, maybe I did that part right. Yeah, I mean this should just work out to, this should just be this basically, right? Once I take the sum of these. But the only concerning thing is, don't I lose the? Well, no. I guess I still have the Leibniz rule here, whichever way it goes. You see many people who join math late often do specialize in geometry topology. Why so? I have no idea. I haven't made that observation myself, so couldn't tell you. Yeah. We're almost out of coffee, so the stream will be ending soon. Let's see. Okay, so we have the associated graded sheaf. Actually, I was trying to look up the definition of graded sheaf. Well, maybe it's in this book. I mean, this is just a sheaf with a compatible grading. I just don't know if there's an extra part of the definition I'm missing. But then we have a relative spectrum as well, so maybe we should try and go through this theorem at one point. So we want to show, put this here, that the relative spectrum of our graded sheaf recovers the cotangent space. That's going to be pretty important for other things later, because one of the things I'd like to talk about eventually are symbols and characteristic varieties of the D module. So let's double check here. What do we have? So we have the graded sheaf. Given a coherent dx module with good filtration. Okay, that's not the definition, but and what is our definition? What is our formal definition of the let's see here. Relative spectrum. If S is a scheme, G is a sheaf of commutative OS algebras, which are quasi-coherent as sheaves of OS modules, then for any affine, the spectrum is a U scheme. So we take the spectrum of this thing by gluing the spectra over all affine U, one obtains the G scheme, the relative spectrum. Oh, okay. Okay, so we're basically just gluing together. We're just gluing together. So glue together the affine schemes for U as we go over all U in X. So intuitively that makes sense, right? Because I mean, what is this thing? Well, the one thing I'm worried about is maybe there's something else going on here with the graded part of this instead of just saying the dx. But I mean, this is built out of this is built out of, you know, our structure sheaf and then also these differential operators, and it's this part that can be interpreted as coordinates for things on our cotangent bundle. This is basically saying differential operators commute up to lower order ones. Aha. Right. So if you take the associated graded, you still get the same abelian group, but force commutation on the nose. Hence, you get the symmetric algebra sheaf, whose relative spec, in general, is the underlying vector bundle. Right, so the graded sheaf, are we taking... what are we taking for the graded sheaf? Oh, is the graded sheaf, are we taking the sum of the quotients? Is that what we're doing to force the commutativity? We're going like... We're going like that? Associated graded is the sum of the subquotients. Right. Okay. Great. Great. Okay. Well, I just finished my coffee, so I think we will leave it there for today. It's been great talking to you all. Time to go prove some theorems. It's Tuesday, you know, so time to ramp up, get at it, and I'll see you all pretty soon.